Hello everyone. Today I'm going to talk about efficiently solving a fundamental graph problem, the minimum cut problem, in the PRAM model of parallel computation. This is a joint work with Sagnik, Mukhopadhyay, and Danupon Nanongkai at KTH Stockholm. In this talk, we will overview the first parallel weighted min-cut algorithm that has low depth and is work optimal in the regime of non-sparse graphs. The techniques involved are a parallel approximation algorithm for weighted min-cuts that performs less work than previously known in the regime of non-sparse graphs, and a proof that the minimum to respecting cut problem can be parallelized work optimally with low depth. Hopefully, this will become clearer by the end of the presentation. Next, I will define the minimum cut problem, describe the parallel model of computation used, and then proceed to state our main result. The minimum cut problem is a classic graph optimization problem. Given a weighted graph with n nodes and m edges, a cut is defined as a set of edges whose removal disconnects the graph, and the size or value of a cut is defined as the total weight of edges in the cut. Now, the minimum cut is the cut with the smallest value out of all possible cuts in the graph. In the figure, it can be checked that the middle edges define such minimum cut. The goal is, given such a graph G, to find the minimum cut of the graph. Next, I will briefly overview our parallel model of computation, the parallel random access machine or PRAM model. The PRAM is proposed as a natural parallel extension of the sequential RAM. In short, it consists of a set of independent processors, each a sequential RAM, that communicate through an unbounded shared memory by means of reading and writing instructions. To analyze the complexity of PRAM algorithms, we use the work and depth measures. The work is defined as the total number of operations performed by all processors, and the depth as the number of parallel steps required by the entire computation. As for efficiency, we say a PRAM algorithm is work optimal if it uses roughly the same number of operations as the best sequential algorithm for the same problem. This is desirable in that a work optimal parallel algorithm is efficient even when there are not many processors available. Moreover, a parallel algorithm is considered fast if it has polylogarithmic depth. Throughout this talk, we will focus only on the work complexity measure and assume all parallel algorithms discussed have depth at most log cube n. I will now quickly review the lay of the land in efficient randomized algorithms for the weighted minimum cut problem in the parallel setting. Throughout, n is the number of vertices and m is the number of edges. Almost 30 years ago, Kurt was the first to obtain a parallel min-cut algorithm for weighted graphs with polar logarithmic depth. It uses n squared log cube n work and is a parallelization of his classic sequential algorithm, which works by randomly contracting edges. Later, Kurt was able to improve this result to n squared log n work, but it was only recently that Geisman and Giannini were able to break this quadratic dependency in the number of vertices by giving a parallel min-cut algorithm that requires only near linear work in the number of edges, namely m log to the 4th power n work. They obtained this result by parallelizing the then fastest sequential algorithm, also by Kurt, which has complexity m log cube n. This is a log n factor less work than the parallelization by Geisman and Giannini, thus leaving open the question of a work-optimal parallel min-cut algorithm. Since then, there have been two important developments in sequential min-cut algorithms for weighted graphs. The first is an algorithm by Gawrychowski and others who managed to improve the runtime of Kargar's near-linear time algorithm in a logarithmic factor, obtaining a time bound of m log squared n. The second development, which was obtained simultaneously, is an algorithm introduced by Mukhopadhyay and Nanongkai and then modified by Gawrychowski, who obtained a bound of m log n plus n to the 1 plus epsilon work for any epsilon larger than 0. It is important to highlight that this result dominates all previous results in the regime of non-sparse graphs, namely graphs of size at least n polylog n. In this regime, one can always pick an epsilon such that the running time is smaller than m log squared n. Throughout this talk, we use non-sparse to refer to graphs of size at least n polylog n, and sparse for graphs of size at most n polylog n. The question that we set out to answer in this work is if these improved sequential running times can be matched in the parallel setting. In this work, we answer the question affirmatively. In the PRAM model, we improve Geisman and Giannini's algorithm by parallelizing the SOSA 2020 algorithm by Gawrychowski and others. Our result is highlighted here in green. The parallel algorithm has the same m log n work, and for graphs of size in the order of n to the 1 plus epsilon, it improves the previous best work by Geisman and Gianninazi by a log-cube n factor. A similar result was also achieved independently by Anderson and Blaloch, who parallelized the ICALP 2020 algorithm by Gawrychowski, here highlighted in orange. The work of their algorithm matches the corresponding sequential running time, making this result work optimal in the regime of sparse graphs. In the regime of non-sparse graphs, on the other hand, our algorithm is work optimal, as its work matches the running time of the best sequential algorithm for the same problem. I will now discuss the technical overview of our algorithm, where I will point at the specific contributions made in this work. Given a weighted graph, our algorithm, like the others discussed in the last few slides, is based on a framework developed by Karger that consists of 4 main steps, which must be sequentially executed one after the other. First, we have to compute a constant factor approximation of the mean cut. Second, we have to construct a sparse subgraph of the input graph that approximately preserves the mean cut value. In Karger's framework, this is referred to as a skeleton graph. Third, we must find a special collection or packing of spanning trees such that at least one of them satisfies a particular property whose definition we're not concerned with in this presentation. And fourth, for each of the trees, we have to solve a more constrained version of the mean cut problem called the minimum two respecting cut problem. Hence, towards designing an efficient parallel algorithm, one has to give efficient parallel algorithms for each of these steps individually. In the one hand, the approximation and two respecting steps are each known to require n log-cube n work. On the other hand, the skeleton and packing steps are known to be easy to parallelize with polylogarithmic depth, and in the non-sparse graph regime, this can be computed with at most m log n work. This means that the approximation and two respecting steps are the parallel bottlenecks towards a work-efficient mean cut algorithm. In the independent work of Anderson and Blaloch, the work of these procedures is improved to the bounds highlighted here in orange, which proves sufficient for their purposes. Likewise, our own contribution, here highlighted in orange, is twofold. For the approximation step, we design a parallel mean cut approximation algorithm with low depth that in the regime of non-sparse graphs requires only m log n work. This algorithm by itself might be of independent interest. For the two respecting step, we show that the corresponding subroutine of the sequential state-of-the-art algorithm for non-sparse graphs by Gawrychowski and others can be parallelized work optimally with low depth. Putting these results together into Karger's framework, we obtain our main result. In the remaining of this talk, I will try to give an overview of our improved parallel algorithms to find an approximate mean cut in weighted graphs. For brevity, I will skip the details of the parallelization of the two respecting steps. Before continuing, however, a few remarks are in order. First, I'd like to remind the viewer that our parallel algorithms developed in this work are for weighted graphs. However, one can also see a weighted graph as an unweighted multigraph, meaning that an edge of weight W is seen as W unweighted copies of itself. In the remaining of the presentation, we will often switch between these two representations. I would also like to remind the viewer that all algorithms discussed so far require log-cube n depth, and for this reason, we restrict to mentioning only the work complexity of our algorithms and procedures. Before going all technical into the algorithm, we will build some intuition into the problem we wish to solve to approximate the mean cut, starting with the concept of a graph skeleton. Take a graph G with n nodes and m edges, and then sample each edge of G with some probability p. We call the induced subgraph a skeleton graph of G. An important result by Karger is that so long as the sampling probability is sufficiently large, every cut in the skeleton takes up roughly its expected value. So in particular, suppose we compute the mean cut value of the skeleton. Karger's theorem tells us that this value will be within 1 minus epsilon and 1 plus epsilon times its expected value, which one can easily check that is p times the value of the mean cut in the original graph. Thus, the value of the mean cut in the skeleton divided by the sampling probability is a 1 plus minus epsilon approximation to the mean cut value in the input graph. Hence, the problem of finding our mean cut approximation is essentially reduced to finding a correct sampling probability p with which to build a skeleton, where we can then compute the mean cut value. Now, Karger tells us that it is enough to sample with a probability of value at least of order log n, divided by a constant underestimate of the mean cut value for this theorem to be correct. For the sake of simplicity, we can take this to be 100 log n divided by this approximate mean cut value. In the remaining of the presentation, we will call this the correct probability and denote it by P subindex S. At first glance, it might seem circular in that we appear to require an approximate min-cut value to get a correct sampling probability, and we need a correct sampling probability to find an approximate min-cut value. In the sequential setting, this problem can be solved easily by first running a linear time approximation algorithm by Matula, and then use the found approximation value to construct a skeleton with correct sampling probability, thus avoiding the recursive argument entirely. In the parallel setting, however, this does not work, as there is no parallel variant of this algorithm that has near linear work. And in fact, there is no parallel approximation algorithm for weighted graphs that takes less work than computing an exact min-cut. So how can we escape this loop and find the correct sampling probability efficiently in parallel without having explicit knowledge of the min-cut? Naively, we can try to find the correct sampling probability as follows. First, we fix a value for P, say 1/2, and then construct its corresponding skeleton and then find its minimum cut. From Kargar's theorem, we know that using the correct probability PS, the value of the min-cut in the skeleton should be 100 log n. Therefore, if we find that the min-cut in the skeleton has roughly this value, then we have found that our chosen P is the correct sampling probability, and we can proceed to find our min-cut approximation. In the paper, we formalize this argument by showing that the min-cut in the skeleton sampled with correct probability is likely between 75 log n and 125 log n, which gives us the means to accept or reject the choice of P. Now, towards turning this intuition into an efficient parallel algorithm, we use the notion of a Kcut certificate. Unlike a skeleton, where all cuts are approximately preserved, a Kcut certificate preserves cuts of values less than k exactly, but cuts of higher value are not preserved at all. In addition, it has only k times n edges. In the figure, it can be checked that the bottom graph H is a 1 certificate of graph G. To construct a Kcut certificate, there is one simple algorithm that consists of iteratively finding and removing spanning forests for a total of k times. This algorithm can be easily parallelized by plugging in a parallel spanning forest procedure. We are now ready to outline our parallel approximation algorithm. For this purpose, we begin by reviewing a naive algorithm and then describe the steps we took in the paper to turn this into an efficient parallel algorithm. As a first step in the naive algorithm, given our input weighted graph G, we construct a collection of log n skeletons by sampling the first with probability 1/2, the second with probability 1/4, and so on, where the ith skeleton is sampled with probability 1 divided by 2 to the ith power. Remember that we see a weighted graph as an unweighted multigraph. So by sampling each unweighted edge naively, it is easy to see that these skeletons can be constructed in parallel with capital W log n work, where capital W is the total amount of edges in the multi-graph representation, or equivalently, the total weight of edges in the weighted graph representation. For the second step of the naive algorithm, we know that the skeleton sampled with correct probability PS has min-cut value roughly 100 log n. Hence, we can further sparsify our skeletons while preserving their desired min-cut value by constructing for each of them in parallel a Kcut certificate with k equal to, say, 200 log n. This can be done in parallel with only m log n work per certificate construction, and hence m log squared n work in total. As the third step in the naive algorithm, we compute the min-cut value in each of the certificates in parallel, which only takes n polylog n work because each certificate has only n polylog n edges. So finally, we search for a layer I in this hierarchy whose min-cut value is roughly 100 log n and proceed to compute the desired min-cut approximation. We see from the schematic that towards an efficient parallel algorithm, one must lower the work required for 1, sampling the collection of skeletons, and 2, the construction of the certificates. Towards solving the first bottleneck, one could simply assume that we can sample each weighted edge binomially with constant work, which implies an overall work band of only m log n for the skeleton's construction. In our paper, we don't make such assumption, yet we can still assume that there are up to log n unweighted copies of each edge across the entire collection of skeletons because of a trick we call truncation. The idea behind truncation is to remove the excess weight of every edge across the sampled hierarchy, as we know from Kargar's theorem that up to order log n weight can be in a minimum cut. For brevity, we skip the details in this talk, but we refer the interested viewer to the paper. Now, if there are only order log n unweighted copies of each edge across the collection, then the total sampling work is bounded by the total number of unweighted edges across the entire collection, which is m log n. Our goal now is to improve the work required for the parallel construction of the certificates. Informally, for every weighted edge in the original graph G, we wanted to take part in at most order log n many certificate computations. Our approach towards this goal is twofold. The first trick is, instead of sampling each skeleton in the collection independently, to subsample their edges from top to bottom in a hierarchy as follows. Given our input graph G, for the first level or layer in the hierarchy, we define G1 to be a subgraph of G, where G1 includes every unweighted edge of G independently with probability 1/2. For the second layer, G2 is a subgraph of G1 with its edges sampled from G1 with probability 1/2, and so on for the up to log n layers in the hierarchy. At layer I in the hierarchy, we can see the subgraph Gi as a skeleton of the input graph constructed with sampling probability 1 divided by 2 to the I power. Assuming a constant sampling scheme or the truncation trick discussed before, the total work required to construct this sampled hierarchy is still m log n. The reason for subsampling will become clear in the next slide when we discuss the second trick towards the goal of reducing the certificate's work bound. The second trick, which we call discarding, consists of constructing the certificate hierarchy while keeping a strict budget on the number of times a weighted edge participates in a certificate computation. For this, we work in a bottom-up fashion as follows. First, we construct the certificate HK by iteratively finding order log n many spanning forests as in the standard certificate algorithm. Then, for certificate HK-1, we discard the edges from GK-1, which have already taken part in order log n many spanning forest computations, which we can keep track of by means of keeping a global counter. Then, we find order log n many spanning forests as before, and combine them with the certificate found in the lower layer to obtain our certificate HK-1. Here is when we can appreciate why we needed to construct our sample graphs by subsampling. It was so we can reuse the certificates we have found in the lower layers and recover the effect of edges that might get discarded in the process. In other words, subsampling allows us to discard edges without it impacting the validity of our certificates. Now, we repeat this process upwards in the hierarchy until we reach the first layer. Because every edge participates in at most log n many certificate computations, we can bound the total work of constructing this hierarchy as the total number of edges across, which is m log n. Therefore, subsampling edges together with the discarding trick improves the work required for the parallel construction of the certificates as desired. And in the end, we get a parallel approximation algorithm that performs m log n plus n polylog n work, which in the regime of non-sparse graphs is order m log n. This concludes the technical part of the talk. I will now summarize this presentation and conclude by stating a few open problems. In this talk, we have overviewed the first parallel weighted min-cut algorithm that has low depth and is work optimal in the regime of non-sparse graphs. We saw that to improve the work complexity of the state-of-the-art, our work consists of two technical contributions. On the one hand, we develop an improved parallel approximation algorithm for min-cuts, and on the other, we show that the two-respecting step can be parallelized work optimally with low depth. Regarding some open problems, perhaps the most glaring in the context of parallel min-cut algorithms is to lower the depth complexity. We have discussed in this talk how the work complexity of the state-of-the-art could be improved, but not its depth. Two bottlenecks are identified. The first is the construction of an appropriate tree packing, and the second is our own approximation algorithm. Both steps require log cube n depth, but all other steps can be done with at most log squared n depth. So to lower the depth of our algorithm, one has to keep track of discarded edges across the certificate hierarchy in a parallel fashion. And also an improved parallel algorithm for the respecting step, for the packing step, would imply an overall improved min-cut algorithm. It would also be of interest to develop implementations of these and other algorithms, both parallel and sequential, to compare their performance on real graph instances. There are not many implementations of parallel min-cut algorithms. The only implementations known to us are of Keisman and Janinatz's algorithm, the classic algorithm of Karger and Stein, and both heuristic and exact algorithms recently developed by Hensinger and others. And this concludes this presentation. Thank you.